Welcome to this technical overview of multi-instance GPU and virtual compute server. This video explains how GPU partitioning techniques improve resource utilization and enable multiple workloads to share a single GPU efficiently. The A100 GPU is based on the Ampere architecture and provides high compute capability for data center workloads. It includes 40 gigabytes of GPU memory, 108 streaming multiprocessors, and over 300 teraflops of tensor core performance, supporting AI, data analytics, and high-performance computing applications. A common limitation is that many GPU workloads do not require the full capacity of an A100. When running demos, proof-of-concept code, or smaller models, only a fraction of the available memory may be used. Without GPU partitioning, the entire GPU is allocated to a single user, leaving a large portion of resources unused. This leads to low utilization. Multi-instance GPU, or MIG, allows a GPU to be spatially partitioned at the hardware level into separate GPU instances. Each instance receives dedicated streaming multiprocessors, crossbar resources, cache banks, and isolated memory channels. These separate data paths provide hardware-level isolation between instances. NVIDIA offers two fundamentally different approaches to GPU partitioning. Spatial partitioning with NVIDIA Multi-Instance GPU, MIG, divides the physical GPU into dedicated hardware sections. Each section has its own streaming multiprocessors, cache, and memory slices with hardware-level isolation, creating up to 7 independent GPU instances. Temporal partitioning with NVIDIA VCS takes a different approach by using time slicing to share the full GPU across multiple virtual machines. On GPUs such as the NVIDIA A100, certain vGPU profiles support up to 10 virtual GPUs, but this limit depends on the selected memory profile rather than a fixed hardware cap. Managing MIG involves a straightforward workflow using NVIDIA SMI commands. First, enable MIG mode on the GPU. Then, check availability to see which instance profiles are possible. The unique feature of MIG is two-level partitioning. You create a GPU instance which defines the physical hardware allocation. Then, within that GPU instance, you create one or more compute instances for workload scheduling. This provides both hardware isolation and flexible scheduling. You can dynamically create and destroy instances without affecting others. And when you're done, you remove the partition. This workflow requires administrator privileges but gives you complete control over GPU resources. MIG provides several instance profiles designed for different workload sizes. The smallest, 1G.5 GB, includes 14 streaming multiprocessors and 5 gigabytes of memory, and supports up to 7 concurrent instances. The 2G.10 GB profile allocates 28 SMs and 10 gigabytes, and supports 3 instances. The 3G.20 GB profile provides 42 SMs and 20 gigabytes for 2 instances. The 4G.20 GB profile creates a single larger instance with 56 SMs and 20 gigabytes. The 7G.40 GB profile allocates the full GPU with all available streaming multiprocessors and memory. Virtual Compute Server uses temporal partitioning to share GPU resources across multiple virtual machines through time slicing. Each VM is assigned a vGPU profile with a defined memory allocation. The GPU scheduler distributes processing time among active VMs, allowing idle capacity to be reused by other workloads. This approach supports environments with variable resource demand. The two approaches differ in architecture and behavior. MIG uses spatial hardware partitioning with up to 7 dedicated instances, while VCS uses temporal software partitioning supporting up to 10 virtual machines. MIG provides dedicated compute resources with hardware isolation, whereas VCS shares resources dynamically through scheduling. MIG enables compute instance partitioning within GPU instances and is designed for low latency operation and fault isolation. MIG does not support NVLink multi-GPU communication, while VCS supports peer-to-peer CUDA transfers over NVLink for multi-GPU workloads. Both approaches support multi-tenant deployments and address space isolation, and the appropriate choice depends on performance and isolation requirements. MIG supports heterogeneous partitioning. The GPU's memory and SM slices can be configured in multiple combinations, allowing different instance sizes to coexist on the same device. For example, configurations may include several small instances, a mix of medium and small instances, or a few larger instances depending on workload requirements. This configurability allows the GPU layout to be adapted to different mixes of training, inference, and development workloads running concurrently. GPU partitioning supports several compute workflows. One scenario is a single user running multiple applications simultaneously in separate partitions. Another is a single tenant supporting multiple users, where each user is assigned an isolated partition. A third scenario involves multiple tenants with separate GPU instances allocated to different customers. These workflows are common in shared research, enterprise, and cloud environments where workload isolation is required. GPU partitioning can be applied to parallel hyperparameter experimentation. During model development, multiple configurations may be evaluated simultaneously, such as different architectures, optimizers, or regularization settings. Separate GPU instances allow multiple training jobs to run in parallel on the same device, reducing overall experimentation time. MIG supports multi-user operation, in which several users share a single GPU through isolated instances. Each user runs workloads independently with dedicated resources. An activity in one instance does not affect others. This model is commonly used in shared research and development environments. GPU partitioning allows different workload types to run concurrently on a single GPU. For example, one instance may handle model training, while other instances support inference, interactive development environments, or profiling tasks. Each workload receives a defined allocation of compute and memory resources, enabling simultaneous execution without over-provisioning. Virtualization introduces a measurable but limited performance overhead. Measurements show that VCS running on MIG instances typically incurs about a 5% reduction compared to bare metal MIG. In example inference workloads across multiple instances, VCS maintains approximately 95% of native performance. This overhead is associated with added management and orchestration capabilities such as VM provisioning, migration, and monitoring. MIG is typically used in environments that require predictable performance and strong hardware isolation between workloads. It is suited for multi-tenant deployments that prioritize fault isolation and consistent latency. VCS is commonly applied in scenarios with dynamic workloads, where flexible sharing can improve overall utilization. Both approaches can be combined to balance isolation, efficiency, and operational management. In summary, hardware-based spatial partitioning creates isolated GPU instances with dedicated resources, while software-based temporal partitioning enables shared access through scheduling. Spatial partitioning emphasizes predictable performance and isolation, whereas temporal partitioning improves utilization through dynamic sharing. Combining both methods allows systems to balance performance guarantees with efficient resource use, depending on workload requirements.